Welcome to part 4 of the onboarding series for servo in motion. Safety is a critical aspect of any motion system, but what does it really mean in the context of servo drives? In this session, we'll take a closer look at how safety is implemented, what challenges come with it, and how different approaches can impact machine operation. We'll also explore some common misconceptions, like whether simply cutting power is a real safety function, and discuss how system features such as amplifier I/Os can be leveraged effectively. Let's get started. Let's start with the most basic question. Is safety implemented in our drives? Do we need it? The safety circuit is an integral part of the amplifier's hardware. It is impossible to add safety functionality to an amplifier that wasn't designed for it. Servo amplifiers with built-in safety features contain a dedicated electronic circuit responsible for safety operations. This means that safety cannot be retrofitted into an amplifier that lacks this design from the start. The table presented shows various safety functions and the servo drive series that support them. Only the NMRJ5 and NMRJ-ETH series come standard with advanced functional safety, both via network and hardwired safety. Safety functions can be triggered through a network using an appropriate PLC and communication protocol, such as CC-Link I/ETSN or CC-Link I/E-Field. CC-Link I/ETSN is used for MRJ5 and MRJ-AHS servo drives, while CC-Link I/E-Field is used for MRJ4 drives. These protocols allow safety signals to be transmitted over the network, eliminating the need for additional wiring and simplifying integration in safety applications. This eliminates the need for additional wiring and simplifies integration in safety applications. Alternatively, safety functions can also be triggered via hardwired safety, where the signal is transmitted through a safety I/O module in the PLC or a standard safety relay. In this case, safety signals are physically connected to the servo amplifier, such as through the CN8 input. The choice between network-based and hardwired safety can impact the final SIL level achieved, so it is essential to consult the safety documentation for the specific servo drive series during the application design process. How do customers approach safety in applications? Not all safety measures are truly safe. While some solutions may seem functional at first glance, they often fail to meet actual safety standards. Proper implementation demands a well-designed system that ensures reliability and compliance. Sometimes, customers attempt to implement safety by simply cutting power to the servo amplifier. However, this approach does not meet proper risk assessment standards because it lacks functional safety monitoring, redundancy, and confirmation that power has actually been disconnected. For example, in the event of a contactor short circuit. Additionally, it does not undergo proper safety testing, which contradicts EIC directives. While power disconnection can be implemented in a standards-compliant way, it must be done using a safety-rated relay or contactor with dual confirmation. If a client does not require SIL certification, it is still recommended to use the EM1, EM2 force stop functions, which are standard in our amplifiers. This feature allows the drive to decelerate or cut off power when triggered. EM1 acts like STO, safe torque off, but without safety certification. EM2 acts like SS1, safe stop 1, but without safety certification. Even without SIL compliance, EM1 and EM2 ensure a structured stop sequence, reducing stress on the system and improving operational safety. Safety in servo drives is more than just cutting power. It's about proper design, compliance with safety standards, and understanding the real risks in an application. The standard European version of our servo drives is identified by the RG suffix at the end of the servo amplifier's model name. These servo amplifiers feature two encoder inputs, CN2, used for connecting the servo motor, and CN2L, which supports fully closed-loop functionality by allowing the connection of an external encoder. This provides additional feedback, for example, from a mechanical system, ensuring more precise motion control. External encoders can be used, for example, to connect a linear encoder that reads the position of a ball screw module, providing the servo amplifier with real-time feedback on the actual position of the carriage. The amplifier then compares the values from the linear encoder and the motor's rotary encoder, calculating the deviation and adjusting the motor's position accordingly for improved accuracy. The external encoder can also be a rotary encoder. Multi-axis amplifiers also have 2 or even 3 encoder inputs, but in their case, each input corresponds to a specific servo motor connected to the amplifier. When using third-party motors with our amplifiers, their encoders should be connected to the CN2 input for absolute encoders or to the CN2L input for incremental encoders. Each servo drive series supports different encoder protocols. For the MRJ5 series, the standard protocol is the Mitsubishi encoder protocol, used for Mitsubishi electric manufactured encoders. Additionally, NDAT 2.2, VIS, C, and ABZ phase protocols are supported for third-party motors or fully closed-loop functionality. Each servo amplifier is equipped with an input-output I/O connector, which plays a crucial role in applications. These I/Os are commonly used for limit switches, proximity, DOG sensors, EM1, EM2 force stop functions, mark detection signals such as the touch probe in MRJ5, and free digital signals for connecting other devices. The number of available signals depends on the amplifier version, with different series offering 20, 26, or 50-bit I/Os. The specific I/O configuration for each model can be found in its hardware manual. Various accessories can be connected to servo amplifiers, including EMC filters to reduce electromagnetic interference, external braking resistors to dissipate regenerative energy when necessary, and terminal blocks for easier I/O connection, except in MRJ5HS and NEMSRJET HS series. Older servo drive series like MRJ4 and MRJ require a backup battery to maintain encoder position data after power loss, whereas MRJ5 and MRJET no longer need batteries for this function. EMC filters help mitigate electromagnetic interference, EMI, that can occur in electrical systems and should be used in almost every servo amplifier application, especially in DC bus systems. Braking resistors are used to dissipate regenerative energy generated during servo drive braking. Most servo amplifiers have a built-in resistor, except for 100 watts models, so in most cases, an external one is unnecessary. However, if the calculated regenerative energy exceeds the built-in resistor's capacity, an external resistor must be used as determined by the motorizer software. Terminal blocks simplify the connection of I/O signals, making installation faster and more efficient. They should be used when I/O signals are required or when installation speed is a priority over cost. Batteries allow the storage of absolute position data from the servo encoder after power is turned off. They are essential when position retention after a power loss is crucial and should be used with multi-axis amplifiers. However, MRJ5 and MRJET with HK series rotary motors do not require batteries for this function. We've explored how safety is integrated into amplifiers, common misconceptions, and how different approaches can impact machine operation. As always, making the right choices in safety is crucial for both protecting equipment and ensuring operator well-being. Thanks for watching, and see you in the next session.